Hello students, now we turn to the DPCM, that is the next version of the PCM, that is pulse code modulation, and DPCM is nothing but the differential pulse code modulation. Let us start with the introduction. The differential pulse code modulation is the technique of analog to digital signal conversion. So this technique similar to the analog to digital conversion process. This technique samples the analog signal and then quantize the difference between the sampled value and its predicted value and then encode the signal from a digital value. So before discussing the pulse code modulation, we have to know the demerits of the pulse code modulation. So before going to start with the DPCM, we should know what are the drawbacks of the PCM system. So in PCM, the samples of the signal are highly correlated with each other, and the signal's value from the present sample to the next sample does not differ by the large amount. So in PCM system, suppose the previous samples and the next samples, these are the two samples if you consider as example, but the difference between these two samples and the next two samples are not in the large amount. The adjacent samples of the signal carry the same information with the small difference. When these small samples are encoded by the standard PCM system, the resulting encoded signal contains some redundant information bit, and this can be explained by the following figure. So this is the figure. Suppose this is the first sample and this is the second sample. So difference between these two samples are not much, and the difference between these two are quite similar to the previous difference. Uh, Let us take the next two samples. So difference between these two samples is again similar, correlated with the difference between these previous two samples, and so on. So in this figure, the continued time signal x of t is denoted by the dotted line. So x of t is denoted by the dotted line, and this signal is sampled by the flat top sampling at the interval ts, 2 ts, 3 ts up to the n ts. We already discussed the types of the sampling in previous videos. The sampling frequency is selected to higher than the Nyquist rate. So for the sampling, so your sampling frequency is greater than twice of the 2W. These samples are encoded by using the 3-bit or 7 levels PCM, and these samples are quantized to the nearest digital label shown by the small circle in this figure. So the quantization is labels are shown by the small circle. The encoded binary value of each sample is written on the top of the sample. Just observe the figure, and at the samples taken at the 4ts, 5ts, 6ts are encoded the same value, and this information can be carried by one sample value, but three samples carrying the same information means redundant. Now let us consider the samples at 9ts. So 9ts, the samples at 9ts, that is 101, and 10ts. The difference between these samples only due to the last bit, and the first two bits are the redundant, since they do not change. So in order to make the process this redundant information and to have the better output, it is an intelligent decision to take the predicted value and assumed from the previous output and summarize them with the quantized value, and such process is called as a differential PCM or DPCM techniques. So principle of the differential pulse code modulation is, if the redundancy is reduced, then the overall bit rate will decreases, and the number of bits required to transmit the samples will also reduce. And this type of the digital pulse modulation technique is called as a differential pulse code modulation. The DPCM works on the principle of the prediction, and the value present sample is predicted from the previous samples or the difference between the previous samples, and the prediction may not be exact, and it is very close to the actual sample value. So in this figure, the sampling is taken plus TS, 2 TS, 3 TS, 4 TS likewise. So difference between 2 TS and TS. So some value is predicted. This value is fed back to the for the taking the difference between the next two. So this is the same difference, that is 1 0 and 1 0. Smaller difference is available. Again for the 4 TS, 5 TS, 6 TS and 7 TS, same difference is available. So the sampling bit or the bit available or bits assigned to these samples are the same. Again, the next samples can be predicted by the difference between the previous two samples, and in this way the DPCM works. So differential DPCM or PCM for the samples that are highly correlated when encoded by the PCM technique leave the redundant information behind, and to process this redundant information and to have the better output, it is wise decision to take the predicted sample value assumed from its previous output and then summarized with the quantized values, and the such process is called as a differential PCM or DPCM technique. So let us consider the DPCM transmitter. The DPCM transmitter consists of the quantizer and predictor. So this is the quantizer and predictor with the summer circuits. And this is the block diagram of the DPCM transmitter. So X of NTS is the sampled signal input, and the output is fed back through the predicted value. So this output is, by summarizing this output, is the signal is U of NTS. It is again fed back to the, by predicting, fed back to the sum for the summation, and difference between these two is nothing but E of NTS. And after the E of NTS fed to the quantizer, so you will get the V of NTS. So the first V of NTS is given to the summer, as well as the output from the predictor is again given to the summer. So again the summation will be done and U of NTS will be available. So X of NTS is the sampled signal, X cap of NTS is the predicted sample. So this is predicted sample. E of NTS is the difference between the sampled input and predicted output. It is also often called as a prediction error. So this is prediction error, this is sampled input, and this is the predicted output. V of NTS is the quantized output. So output of quantizer is nothing but the V of NTS. U of NTS is the predictor input which is actually summer output of the predictor output and quantized output. So U of NTS is the predicted out is the summation of the output, quantized output and the predicted output. So you will get the U of NTS. The predictor produces the assumed samples from the previous output. So predictor gives the previous output and the previous outputs, assumed samples and from the previous output of the transmitter circuit, and input to this predictor is nothing but the quantized version of the input signal. So input to predictor is nothing but the quantized input signal. So quantized output is represented as V of NTS is equal to quantization of the error signal E of NTS. So E of NTS is nothing but E of NTS is nothing but the summation of these two signals, that is X of NTS plus X cap of NTS. So E of NTS plus Q of NTS. So Q of NTS is nothing but the quantization error. So V of NTS, that is predictor input, is the sum of the quantizer output and predictor output. So predictor input U of NTS is nothing but the X cap of NTS plus V of NTS. So U of NTS is equal to X cap of NTS as it is, and V of NTS is the previous equation, that is E of NTS plus Q of NTS. So V of NTS is nothing but Q of NTS as it is, but X cap of NTS plus X of E of NTS is nothing but X of NTS, and the same predictor circuit is used to decode decoder to reconstruct the original output. So same predictor circuit can be used. So this is the DPCM receiver. The block diagram of DPCM receiver consists of the decoder, a predictor, and the summer circuit. This is the block diagram. So this is the input BNTS, which is applied to the decoder. So you will get the V of NTS. V of NTS is added with the predictor output X cap of NTS. After the summation, you will get the U of NTS. Again, U of NTS is fed back to the predictor. So in this way, we can reconstruct the original signal. So notation of this signal is same as the previous ones. In the absence of the noise, the encoded receiver input will be the same as the encoded transmitter output. As I mentioned before, the predictor assumes the value on the previous output. So predictor predicts the output by taking the history or by checking the history of the previous output, sorry, and by maintaining or by collecting the correlation between the previous output, the predictor predicts the next output or the bits for the output. The input is given to the decoder is faster, and then output is summed up with the output of the predictor and to obtain the better output. So this is about the DPCM transmitter. I repeating that the DPCM is nothing but the differential pulse code modulation. In pulse code modulation, the analog input signal is um, firstly given to the sample and hold circuit, then quantizer, then encoder. You will get the pulses, and that pulses assigns the symbols. So the data rate is highest, and that data rate um, can be decreased by the DPCM, because the DPCM uses the predictor, and predictor gives the output by checking or by taking the difference between the previous two samples. So so bit required bit is less, so the data rate automatically decreases. So the comparison of the, now you will get the clear idea regarding the PCM and DPCM. So these are the parameters. The second column is nothing but the PCM, and third column is nothing but the DPCM. As per the parameter wise, we can compare the number of bits required for the PCM is 4. It uses the 4, 8 or 16 bits per sample, and in DPCM it is less than PCM bits. Labels and step size. In PCM, the fixed step size cannot be varied, but in DPCM, the fixed number of labels are used. Bit redundancy, it is present in the PCM system, and in DPCM can be permanently removed. Quantization error and distortion. In PCM, the quantization error and distortion is depends upon the number of labels used. In DPCM, the slope overload, distortion, and condensation noise are present but very less as compared to the PCM. So PCM have the more distortion and noise, but as compared to the PCM, DPCM it is less. Bandwidth. The higher bandwidth has been required since the number of bits is present. In DPCM, the lower than the PCM bandwidth because the number of bits are less. Next, complexity. uh, Feedback, no feedback in transmitter and receiver section, but in DPCM the feedback exists because predictor uses the previous output for predicting the next output. Complexity, the PCM system is complex, DPCM system is the simple one. Signal to noise ratio, it is good in case of the PCM, but it is fair in case of the DPCM. Next, application of the DPCM. DPCM technique mainly used for the speech, image and audio signal compression. DPCM conducted on the signal with the correlation between the successive samples leads to a good compression ratio. So it is used in the on signals with the correlation between the successive samples. In images, there is a correlation between the neighboring samples. In video signals, the correlation between the same samples in consecutive frames and inside the frame. So in this kind of the signal, the DPCM can be used in the speech, image and audio signal compression. So specifically the DPCM is used for the compression of the signal. The next application is this method is used for the real-time application because feedback is available, as well as to understand the efficiency of this method of medical compression and real-time application of medical imaging such as telemedicine and online diagnosis. It can be used. So therefore it can be efficient for lossless compression and implementation for lossless or near lossless medical image compression. So this method is again used in the medical imaging application for the compression purpose as well as for the real that is real time application of the medical imaging such as a telemedicine or online diagnosis. So it can be used. Next, the advantages of the DPCM. So, as the difference between the sampled signal X of NTS and the predicted output X cap of NTS is being encoded and transmitted by the DPCM technique, a small difference voltage to be quantized and encoded. So, the number of bits required for the small difference is again less, and this process is requires the less number of the quantization levels, so less number of bits is used to represent them as compared to the PCM. So the signaling rate and bandwidth of the DPCM system will be less than the PCM system. So because the same difference is available for the many pulses, so the same bits can be assigned, so the automatically the signaling rate will be decreases, and as signaling rate decreases the bandwidth will also gets decreases. So these are the some advantages of the DPCM over the PCM. Thank you.